Hello, can you hear me?
Okay, we have some people here. Zoom is going to send me to an early grave. Who is here? Okay, I'm glad you got in. Okay, we're missing one person who was actually the only one who made it into the other room. Apparently, she could get in on mobile, but not on desktop.
Uh-oh.
And I don't know why that is. So we're just going to continue to use this link until, I guess, I'm going to have the front page updated because you guys got in now, and this is okay. I'm sorry. This is not how I wanted today to go.
Well, I had said, could it be possible you had an expiration date in the other Zoom room? Because sometimes they have them.
I double checked. It's not an expiration date issue. The room seems to be functioning perfectly on Zoom's end. I had them look at it, and they're like, yeah, everything seems to be fine. And then somebody else just got into the room like 10 minutes ago on mobile, but could not get in on desktop when she tried. And we're going to wait for a couple of minutes. I'm emailing her now.
This is Blake. I don't know how to change. I've tried so many times to change my wife's name to my name, and it's just not working.
Yeah, I don't know why. I notice every single time, and I'm like, why does it keep doing that to you? Zoom has just not been kind this semester, and I'm sorry about the delay, and I'm sorry that we're 15 minutes late now.
I hope the other person can get in. I feel really bad that we kind of switched.
Yeah, well, she wanted to get in on desktop, and then she couldn't. She tried, and she came back in on mobile, and was like, I can't get in. I just hope people could see the announcement. I literally filled out a ticket. I'm kind of PO'd right now. Okay. Okay. If it worked for you, I'm going to assume that the link works for everyone from the announcements. I'm so sad that it wasn't able to. Oh, I have no response. Does this link?
If we have time, can we run over the relative rate of change and that the formula that he gave us that it just, I don't know, it built off of the original rate of change formula? It's really confusing me.
Yes, we can definitely do that. We can probably, sorry, I'm so frazzled, and that's not okay. We have everyone here now. I'm so sorry. I'm so frazzled. This is okay. You can't see anything because I'm not sharing my screen. No, I am. I am. It's just white. Okay. I don't think this is recording. It is recording. Man, it's so liberating to have a functional Zoom room. Okay. We were going to talk about the rate of change formula. What rate of change formula are you referring to?
It's the one where it's d over dt, then ln, and it's got f in parentheses with the t, and then closing the parentheses.
Okay, sorry, my tablet is not plugged in. There we go. Okay, so it is what?
D over dt, and then to the right of that is ln. And then it's an open parentheses with an f, and then another open parentheses with the t, and then we just close the two parentheses. That's what it shows in the book, and that's what he talked about in his, Jan talked about in his Zoom room on Tuesday, but it's just very confusing.
What section is this in?
This is, I believe it's 3.3. And the questions, I believe, start at 20, 29, 30.
Oh, yes. Okay. So this is, we're thinking of this as relative rates of change and not of like average rates of change, right? When you think of something being like a relative rate of change, what are you thinking of? Like, kind of describe to me what a relative rate of change is.
To me, a relative rate of change would be a slope over whatever the function is. So like f prime over f.
Yeah, essentially. So we are essentially comparing the slope of something to the rate of change. No, the slope of something to the original something. And we established that, as you just said, we're thinking the slope, or f prime, over the original, which is the f. And the way that they kind of walk through the derivation is they said, what if f is equal to z? So this is a function we'll call f of t, and this function is equal to z. So this is theoretically z of t. This remains a function, but we're just writing it in this way so that we can think about it in terms of like what if it's considered to be a variable. So if f of t is equal to z, what is f prime of t?
Would it be z?
What is the derivative of, like, if I have y is equal to x, what is the derivative of just x?
X.
Not quite. What about if I had 3x? The derivative of 3x is going to be
3x.
it's just going to be 3.
Oh, 3.
Because if we think about, like, this is x to the 1, and then we're going to subtract 1. If we think about it in terms of power rule, then this is going to be 1 times 3, which is the constant here, times x to essentially the 0, or 1. Does that make sense?
Yes.
Awesome.
I also had a question with the relative change. It was actually broken down as a function, 3x minus 1 all over x plus 2 when x is equal to 1. And it said calculate the relative change function.
Okay. Is this one of the problems in the book, or?
This was actually, yes, this was,
Okay, and the idea is we're trying to find the relative rate of change. Let's do this as a problem once we kind of establish what we're looking at regarding what the relative rate of change is. So we know what happens when we have a constant times x and we take the derivative, we just get the constant, right?
right.
So if I take the derivative of just z, which is really z times 1, what is my derivative going to be?
It's just going to be z.
Just going to be 1.
Oh, well, 1.
Yeah, so if I say that this is z times 1, then my derivative is going to be 1 times the derivative of z, which is going to be 1 times z to the 1 minus 1 times 1, which is going to be 1. Another way to think about this is if I leave it in Leibniz notation, this would be dz dz. And this is not a fraction, but if you think about it like a fraction, which you kind of sort of can, then it's something divided by something, the same thing, which is 1, right? So dz dz is always going to be 1.
Just 1. Okay.
Yep.
Okay. I'm not sure where I got that from. I have a bunch of stuff wrote down here.
Okay.
That I was having some issues with. But we started out on 3 of 3. If you go to problems 45 and 50, where it shows to evaluate the derivative of them, I really got confused. I guess at the point to where when you're trying to get the derivative, the slope, and I was the same way with Jan on Tuesday. I don't understand. Are they just saying? I mean, are they just saying that depending on which way the slope is going, whether it's a negative one or a positive one?
Okay.
If
So
40, 45 and 50.
Yeah. Let me finish with what's happening with the relative rates of change.
Oh, okay.
In this bright red here. Then I can definitely talk about, because that's essentially kind of chain rule stuff, which we can discuss in just like 2 minutes.
Gotcha.
So for the light red here, we're kind of thinking about how we can use what is here, dt, the natural log of f of t, for relative rate of change of f of t. And we're kind of setting it up in that, okay, so we said that f of t is equal to z, f prime of t is equal to 1. So this is truth. Like if I say f of t is equal to z, then f prime of t is equal to 1. Then I can say that f prime of t over f of t, or our relative rate of change, which I'll say ROC, is going to be 1 over z. right?
Right.
But it's going to be 1 over z dz dt, because if you remember, z is a function of t.
I just got lost for a second. 1 over z is the where's the z? Is the z because it's the original function?
Okay, we are going to break it down differently. Okay, so I'm going to still set it up in this exact same way, because you were right in saying that our relative rate of change is going to be our slope divided by where we're at, essentially. I am going to continue to say that we have z is equal to f of t, but I'm going to say that it's a function. Okay? So this is a function z of t. I'm just renaming the function. It's the same thing. Now I have f prime of t. What is f prime of t? It's going to be same thing, right?
Yes.
How do I write this in Leibniz notation?
Is it just dy over dx?
It would be if we had the function y prime of x.
So it'll be
dz over.
dz
Yep.
over dt. Okay.
Okay. So let's put this together now. I have essentially up here, my original function. I flopped them around in my writing of this. So this is going to be in the denominator of something, right? So this is going to be 1 over z, not 1 over z. It'll just be here. I won't even write it like that. I'll write it like this. Here is my f prime of t. Here is my f of t. F prime of t is dz dt, and that is going to be divided by z. And it's going to be, this is like, you can think about it like a fraction, but it's not actually a fraction. So it's not going to behave in the exact same way that a fraction does. So instead of saying divided by z, what I think would be better is for us to say, man, if I have, if I have x times, or rather x divided by 3, I can rewrite this so that it says x times 1/3, right? This is something that everyone feels comfortable doing.
It's not 3 over 1.
X divided by 3.
Divided.
Okay, never mind. It's already 3
Yep.
over 1. It's the reciprocal.
Right.
Exactly. So this is 3 over 1. I take the reciprocal, so x divided by 3 is x over 3. X times 1/3 is x over 3. So instead of saying dz dt divided by z, because I have to treat dz dt with like care, I'm going to say this is dz dt times 1 over z. Do you see how I renamed everything for, whatever reason, but I still do have f prime of t divided by f of t in that. Yeah, go ahead.
So the rate of change is just 1 over z is what you're saying?
I'm saying the rate of change is going to be dz dt, because this is our rate of change, right? We have our derivative f prime of t, our derivative z prime of t, our derivative dz dt. I'm kind of like trying to outline like a logical series of steps. If that
I
makes
think
sense.
the confusion is because we're switching, we're kind of essentially renaming the way it is in the beginning, but using different letters instead of actually going through the equation itself. Because I'm a little confused without actually going through the equation and like going step by step and actually working it out.
The reason that they do it like this is that this is kind of like an establishment of how we're going to define things, and we want to be able to generalize it. We want to be able to make it applicable to basically any equation that we run across. So the reason that we're introducing the z's in this point is not because we're planning on keeping them around, if that makes sense. But does everybody follow like this, the logical step? I started off here for nonsense reasons that you don't need to know right now. I changed it to a z because I need to in order to complete this derivation, essentially.
Yes.
I changed it to z because I had to. I turned it into dz dt because that's a rate of change. dz dt is a derivative. When we think derivatives, we think rate of change. And that's corresponding, of course, to my f prime of t up here. And so I said I have f prime of t, and that is divided by f of t, so divided by z, which is the same thing as saying that I'm multiplying by 1 over z. And that's how I end up with where I'm at right now. Is everybody okay? Like, you don't have to love how we got here, but do you understand how we got here?
So it's just a different, all that we're doing is just renaming what the rate of change is.
Exactly.
Is what you're saying?
Yeah. So we're saying that this is equivalent. We're saying that these are the same thing. And we had to go through all of these different steps to get there, but we ended up there. We're not done. We still need to work all the way through it. We don't like having z here. That's not fun for us. So we're thinking, how can we get rid of z so that we don't have to think about z right now? Right? We don't want that. So how about we say, hey, what if I like broke it down into the derivative of something, right? So this is a derivative of z. Is there anything that I could take the derivative of? This is like reverse logic here. Can I take the derivative of something and get 1 over z? What is that something that I can take the derivative of to get 1 over z? There is literally no better way to talk about this but in this kind of language. This is something that you guys are going to have to do later on in this class, this reverse derivative thing. Don't worry about it for right now. But it's basically like, how can I put this together? The derivative of what? What's my question mark?
Wouldn't it be ln?
ln.
Exactly. So I'm setting this up now. This, I don't want to deal with z. I'm going to say that this is going to be the derivative of the natural log of z. I have 1 less z to worry about, right? I reversed my way into this position, and that is the best way to think about it right now. I backed myself up so that now I am looking at a derivative of a natural log. This is the same thing here. They're equal. So I'm still equal to f prime of t over f of t. So now I'm sitting in a better place, but I still don't like that z. So I'm going to go all the way back up here and say that f of t is equal to z of t, right? I'm just going to put f of t back in. A lot of parentheses there. But I'm just saying that z is the same as f. Did I lose you at any point here? Because now we can still say that because everything is still equal, this is a relative rate of change.
So this is almost like a formula that we're putting the equation into, and it will automatically calculate when we complete the formula the relative rate of change?
Yes. This is just a convenient way for us to say, hey, I have a function of t, and then I'm going to take the natural log of that function, and if I take the derivative of that, I've got a relative rate of change. So let's try here in the dark red. If this is my function, I'm going to try to keep the color coded a little bit the same. If this is my function, that is f of t, then, and I want to find a relative rate of change, I could go through and find f prime of t and then f of t, because I have, this is actually f of x, because I have x, but we're going to solve it using this in the yellow here, just because that's kind of what we're doing in this chapter, and because it's really good practice with the chain rule. So, talk to me about what I'm going to do. How am I going to set this up? I'm going to set it up in the exact same way. I have the derivative with respect to t of the natural log of f of x. So this is not t, this is x. Just make sure all your variables are the same, essentially. This is how I'm setting it up. Let's just start putting stuff in. F of x is equal to 3x minus 1 over x plus 2. Right? So, I've got a lot of stuff going on here to take this derivative. I'm going to rewrite this in a space that's not quite so central. Okay, so this is going to deal with both the chain rule and the quotient rule, right? Can you see where the quotient is? Nobody's saying anything, and it's making me really nervous that I've lost all of you. And I'm sorry that I keep like prompting you, but I just want to make sure, like.
Is it 3x minus 1 because it's divided by, it would subtract x plus 2?
It is going to be right here. So our quotient rule is going to be this part here regarding the like divided. And then our chain rule is going to be, here we have a natural log of a bigger function. Okay? So we're jumping in with a really difficult one. Like, I would not have started with this if we started with the chain rule. But I'm going to break it down for you in the exact same way I break down every single chain rule problem. Okay? I'm going to set this up, and I'm going to say I have a function. I'm going to rename it. I know it's ridiculous, but I rename every single function so I don't get them confused. And also, I'm going to color code them because I have a lot of colors of pens online. And I'm going to say that I have a function h of g, which is a little bit different language than what you use f of g in normal chain rule. But hang tight with me. I don't want to use f because f is over here. So I'm going to say this is h of g. And h of g is the function, the natural log of g. And I need 4 different components to run the chain rule. I need h prime, and then I need g, which is a function of x, and I need g prime. And I can set this up as I have the function h of g of x. And the reason that I explicitly say h of g of x in the way that I do is because I want to make it clear that I have a function that is within a function. My outer function in this case is going to be the natural log. And I'm taking that as a function of another function. Can you see where my outer function is as compared to my inner function?
Yes.
Awesome. So I've got it color coded in this way. Now I need to go through and find all of these components. I know that if my h is the natural log, then my g is going to be 3x minus 1 over x plus 2. And I know that I'm going to eventually need to use the quotient rule to figure that out. But for now, I've identified h and I've identified g.
Can I ask a quick question?
Of course.
Are these the same steps that he outlined, the 1 through 4, in his Zoom room for the chain rule?
I haven't seen his Zoom room for the chain rule.
This is where I was a little confused and I hadn't jumped in, is because I just watched the videos that were on the commentary, and
Okay.
this would, and it may not have anything to do with relative rate of change. It's the only issue I'm confused, reason why I'm confused, because they didn't bring natural log in. So that's why I'm just listening instead of jumping in.
Okay. Wait, what was your issue? You said that it wasn't bringing natural log in?
And now I don't know if it's different for relative rate of change or just for the videos that they were going over on the commentary, but the videos were product rule, quotient rule, and chain rule.
Yes, the relative change is somewhere in 3.3.
But it's not in the commentary videos. That's why.
Oh, okay.
The commentary videos just have you go over like the regular, product or a quotient rule with, and chain rule and things like that. So I was a little. I've been kind of.
This relative rate of change stuff, as long as you accept what's here in the yellow, you'll be golden. Understanding why we go from here to here is a more difficult process, which is kind of what we spent the first couple of minutes talking about. But if you are comfortable like following this and saying that the relative rate of change is equal to this thing, then essentially what this becomes is a method for you to practice the chain rule, if that makes sense. Because all of these problems will be set up in a way that you have to practice the chain rule. Because you'll have an outer function of the natural log and an inner function of something else. So let's start finding these different components. Who can tell me what the derivative of the natural log of g is?
G over x.
We're leaving it. We're leaving. This is now the variable.
Okay.
Yep. And we're basically saying, like, if I have the natural log of x, what is the derivative of it?
It'll just be 1 over x.
Yep. So instead of x, I'm going to put g.
Oh, okay.
Yep.
Gotcha.
Because, and the reason I did this, and it is a little strange, but it's because I wanted explicitly to say this is a function of g, because I'm trying to make this simpler for myself. So because this is a function of g and not a function of x explicitly, I'm going to say this is 1 over g.
It's just embedded in our heads, 1 over x. So.
Yep, it kind of is. So now I get over here to the quotient rule, where I'm going to define these two functions, and I'm going to define them differently because I want explicitly to say I have two functions here. One of them I'll call j, and that is a function of x, and j of x is going to be equal to 3x minus 1. Then I have k of x, which is equal to x plus 2. So I can say that g of x is equal to j over k. Is everybody okay with that?
Yes.
Awesome. So then I need to go and I need to find j prime of x. What is j prime of x?
Would it be 3?
Mm-hmm. And then I need to find k prime of x.
1.
Perfect. So I know that my g prime of x is going to be of the form j prime k minus k prime j all over k squared. And that is just the quotient rule, but mixed around a little bit, because the quotient rule they give you on page, I guess in my book it's 158, but the quotient rule they give you is for f over g, and I have j over k. It's the exact same rule. It's just different letters.
Right.
Because I already used both f and g. Okay, so now I have it set up like this. I literally can just plug and chug. I've got g prime of x. It's j prime, which is over here. So it's j prime here. I'm not going to do that in this. I'm going to split again, which is 3 times k, regular k, which is x plus 2, minus k prime, which is 1, times j, which is 3x minus 1, all over k squared. That's x plus 2 squared. Now I get to simplify this. This becomes 3x plus 6 minus 3x plus 1, right? It's an x with a negative sign, over x plus 2 squared. I'm going to cancel that 3x, and this is going to turn into 7 over x plus 2 squared. Yeah, everybody's okay with that?
Yeah.
Awesome. Okay. So I have all of my components now. I'm going to erase a little bit here so that I can like squish it back up. So this is 7 over x plus 2 squared. Okay, so I have the important bits, which are this part, not that, this part, and this part. Because the derivative of this here is going to be equal to the chain rule, which says that the derivative is h prime g of x times g prime of x. And again, I'm just rephrasing the chain rule, which shows up in section 3.3. Okay, so this is where I'm sitting. Oh, go ahead.
Oh, I'm sorry. Is this problem from 3.4?
I don't actually know.
I'm not really. I had a bunch of questions that I wanted to ask today, so I just wrote them down. I'm not even sure where I got this from.
Do we have enough time to do a simpler example? Because this really confused me. I was still trying to work through the relative rate of change at section 3.3.
Oh boy, okay. Let's finish this real quick. Can you identify where I lost you? You can like give me a color where I lost you.
Probably at the blue g of x, where it's the 3x minus 1 and then the x plus 2.
Okay. So that's coming into what is this function, essentially. I need to take the derivative of this here in the yellow. And I'm going to use orange, I think. I need to take the derivative of this, the natural log of f of x. Then I said that it's not f of x. I'm given f of x up here in the dark red. It's going to be the natural log of 3x minus 1 divided by x plus 2, because I want the relative rate of change of this, right? So my question here is I want the relative rate of change of this function. How do I get it? I'm going to take the natural log of this function and then take the derivative of that whole thing. Does that make sense? The answer can be no. The way that we set that up is we said we have our relative rate of change. We said that it is going to be equal to the derivative of something, the derivative of the natural log of the original function, right? So if my original function is x, how do I do this? This is going to be f of x now, not f of t. So my relative rate of change is going to be the natural log of my function, which is going to be x. I'm just going to say that if f of x is equal to x, I can just put x in right here.
Okay.
And then I can say the derivative of the natural log of x is going to be what?
1 over x?
Yep. So my relative rate of change at any point x, theoretically, in this function is going to be 1 over x.
I think where I'm confused too is so far all we've done is the derivative of g of x. We haven't gone to the natural log yet.
We have not, no.
Okay. So we actually haven't gotten the final answer quite yet.
Nope.
No.
But how are you feeling with this in the orange right here? Like if I have a simpler function that is just f of x is equal to x, does that make sense?
Yeah, because you're just doing the inner function first, and then you're going to take the outer function.
Yes. So I have this simple example. I'm sitting pretty right now. I know how to do that. What if I have the function x squared? Gosh, now I'm looking at the natural log of x squared. How could I do that?
Would it just be 1 over x squared?
It wouldn't. Because in 3.3, what we were mostly talking about was the chain rule.
find the derivative of the inner function first, which would be just 2.
Yes, I'm sorry, the chat. I know there was something going in the chat, but it somehow got maximized. Oh, there it is. Cool.
2L on X, would that be, because you pulled the 2?
Not quite. This is kind of where we're getting into the chain rule. Okay, so table what's happening up here for 2 minutes, I guess, because we're going to go through the whole chain rule. Everything up here is on pause. We're going to do this in the orange right now. I'm sorry this is so disjointed. It's a really tough problem to start with. So I have this function that is the natural log of x squared. I have a function within a function. The way that I want to write that is going to be, I have a function, outer function f of my inner function g of x. And I'm just going to repeat that f, okay? Are you okay with me repeating the f? It's just the language that they use in here, so it's the language that I want to use right now.
Yeah.
Okay. So I have f of g of x. Outer function, inner function, variable. I want my outer function to be established. And I want my outer function, I want to like consider this to be, I'm going to think about g of x as just a single thing right now. Just g. Because I want to focus on my outer function. So I'm going to say this is f of g. And I'm going to think about g of x separately. What is f of g? I have to ask myself, what is my outer function in this scenario? Does anyone have any ideas about what my outer function is?
Is it just ln is the outer function?
It's going to be the natural log, but natural logs don't just get to sit out on their own. They always have to be the natural log of something, and that something in this case is going to be g. But if I say that I have the natural log of g, and I want to make sure that these two functions in the blue and in the orange are the exact same, what do I need to say that g of x is equal to in order to make this all make sense? Or rather g of x, just think about this as g. What is g equal to?
X squared?
Yes. So now if I say I have g here, and I say I have g here, and I put g from here into here, I end up with that. So I'm saying the exact same thing, I'm just saying it in a way more messed up way. I'm adding a whole extra step. But the reason I'm doing that is because now I have something of the form f of g of x, because this here g is a function of x. Everybody following me up to this point?
Yep.
Okay. To take a derivative of something of this form, we're going to use the chain rule. And the chain rule says that if I have something that looks like that, if I have f of g, I'm going to color code it again, f of g of x, then my derivative is going to be f prime of g, regular old g, which is now still, of course, of x, times the derivative g of x. So this is the chain rule, which is given to us in section 3.3. Are we happy with this existing?
I am.
Awesome. So if I need to, like, I want to go from here to here, how do I do that? Well, I need three things as far as I can see. I need f prime as a function of g. So f prime of g is how I'm going to write that, because I don't want to think about it as a compound function right now. I just want to think about two separate functions, one within each other, right? I need G, which I'm going to use the right color for. I need G, and I need G prime. So again, this is G of X and G prime of X. So there are three things I need. I've identified F, I've identified G. Put a big old check mark right there. Got that. But I still need F prime and G prime. So my next step is going to be to say, okay, so what is F prime of G? Because I don't want to think about G as something too complicated. So what is F prime of G? If I have the natural log of G, G is my variable, G is changing.
1 over G.
1 over G. What is G prime? I have G of X is equal to X squared. I'm looking for this with respect to X.
It's going to be 2.
It's going to be 2 times.
Yes.
So power rule, I bring that 2 down, and then it's 2 minus 1 on top. So it's 2 times X to the 1. Okay. So is everybody okay with these derivatives? Okay, we're going to put them together now. Because, like I said, I need something that looks like this. F prime of G of X times G prime of X. So, F prime, 1 over G times G prime, 2X. Right? But this is a function still of G, and I need it to be of X. So I'm going to put my original G in where it belongs. So this is 1 over my original G times G prime, which is going to end up being 2X over X squared, which is going to end up being 2 over X. And that is my whole derivative. So, did everybody follow taking that derivative? Now I've said that ddx is equal to, rather, not ddx, ddx of the natural log of x squared. So I took the derivative of the natural log of x squared, and I got 2 over x. So now I have the relative rate of change for this function, originally x squared, right? So the relative rate of change at x is equal to, I don't know, let's say x is equal to 1. What is the relative rate of change?
Would it just be 2 because we're substituting 1 for x?
What about at x is equal to 100?
Would that be 2 over 100?
Mm-hmm. Okay. How are we hanging in here?
Hanging tough.
You are, guys. Really tough. You got this. I believe in you. But you followed this.
Yes.
Awesome. So we followed this. Now let's go back to the crazy guy up top, because we're doing the exact same thing. We're just going a little nuts.
Can I ask you a question?
Yeah, of course.
In the relative rate of change, the formula where it's d over dx, ln, and then f of x, if we just follow the chain rule, this is just a different way of looking at the chain rule, or doing the chain rule, but it's still the chain rule in this form?
Okay. Repeat that. Sorry, one more time.
Are we still following the chain rule? It's just now ln 3x minus 1 over x plus 2.
Yes, exactly. So we have here a two-step problem. We have a chain rule that requires the quotient rule to solve.
No, that makes sense. Yeah, we need to use both rules. Okay.
Yep. So let me erase all of this junk down here and erase my on pause line, because this is no longer on pause. Okay. All right. So let's catch up to where we just were. I'm going to erase some up here. Sorry, I haven't been like going up here because that's where my chat box has been, but I think it might be good to like declutter, and I'm going to rewrite some of this. Okay. So I'm going to go through with the orange and establish where we're at right now. Okay. So we said we have this function that we need to solve. I wrote this in blue for no reason at this point. But here, it's in blue because I want to say that I have an outer function and an inner function. Namely, that if I have the function h of g of x, that I have h of g is equal to the natural log of g, and g of x is equal to 3x minus 1 over x plus 2. So if I take my g and I shove it back where it belongs, I get my original function. So it's the same principle. So I have this function h of g of x, and I want to find its derivative. I need h prime of g of x times g prime of x. This is my derivative formula for the chain rule. So this is basically what I'm saying. I need this, all of these components for, like, this is going to be the derivative. I'm not going to write it in the instantation. I'm just going to write it. Derivative. Okay. So then what I did up here is I said, here's my original function. Here's h prime. Here's my original g. Man, I got to use the quotient rule, don't I? So I use the quotient rule. I split it up. And then I put it all back together, and I got my g prime. Is everybody with me right now?
I got lost at the quotient rule. I get the 3 over 1, but after that I'm lost.
Oh, this isn't 3 over 1, that's just dot. I'm sorry. Okay, so the quotient rule, I kind of wrote out here in terms of j and k. So if we look in the book, it'll give us the quotient rule in terms of f and g. It'll say if I have the function f over g and I want the derivative of that, it'll be f prime times g minus g prime times f over g squared. So that's just what the book spits back at us, right?
Okay.
So I said, I don't have f and g. I already used those variables. I don't want to use them again. I'm going to have k. I'm going to turn all these g's into k's. Right? All of those g's are now k's. And j. All of these f's are now j's. That's j prime, and that is k prime right there. That's what I have right here. So this is just the quotient rule. But for j over k, not f over g. Does that make sense?
Yeah.
Awesome. So, oh, go ahead.
When it's f prime of g and then f g prime, that's kind of where I got confused.
Oh, okay. I swap it around for some reason, I guess. It's the same thing because conceptually speaking, if I have the function f times g prime, I can also say that it is g prime times f, right? Like if I have 1/2 times x, I can also say x times 1/2 because they both equal x over 2.
Okay.
That's just like commutative property. It's one of those properties that I always forget, which is unfortunate. I think it's commutative. It's probably commutative. I'm 90% sure it's commutative property. But I can make this swap. That's just a thing that I can do. I can make it if I'm doing addition. If this is like f plus g, then that becomes g plus f, and those are the same thing. You can't do that with subtraction. F minus g does not equal g minus f. Which is why the order is important of which derivative comes first. Because if I had accidentally swapped these and said, oh, this is j k prime minus k j prime, then that would be wrong. But as long as I have the subtraction in the right location. You feeling a little better about that now? I'm sorry I did that.
Yeah, thank you.
Okay. So then I said, in order to get this, I need another 4 things. I need j prime, I need k prime, and I need j. And this is my original k. So these are the same. But I need 4 things, 1, 2, 3, 4, to make this work. So I found them, j, k, j prime, and k prime. Once I had all 4 of my pieces, then I could get to work. And what I said was, I'm going to set it up in the exact same way that the quotient rule is set up. So that's j prime. J prime is equal to 3. K prime. Not k prime, excuse me, times k. K is equal to x plus 2 minus k prime, which is equal to 1, times the original j, which is equal to 3x minus 1, all over k squared, x plus 2 squared. Then what I did was I distributed this. I said that this is going to be equal to 3x plus 6. And then this is minus the quantity. I'm just going to leave that minus sign where it is now. 3x minus 1. Again, over x plus 2 squared. Then I'm going to distribute this minus sign. So I'm going to end up with 3x plus 6 minus 3x plus 1. over x plus 2 squared. I see a plus 3x and a minus 3x, and I can cancel them out. Then I end up with 7 over x plus 2 squared. And that is what I have over here. So once you put it together, it's just algebra. Thoughts, comments, and concerns?
So it's the derivative of the numerator, which is 3x minus 1. So it's the derivative of that times the denominator.
Mm-hmm.
Then it's minus the numerator times the derivative of the denominator?
Yes. Over the denominator squared.
I'm good with the first part, just the second, not the, I guess the times the oh my God.
That's just the way that the formula is like functions. I wish I could tell you how and why, but we really do not have time to derive the entire quotient rule.
But that's just the quotient rule in a nutshell.
Yeah, this is just the quotient rule. And I apparently am really klutzy with my eraser. So I'm erasing half of it as we speak, but that is literally just the quotient rule. But instead of f over g, it is j over k.
Okay.
Okay. So here we are. We are hanging out. We've got 4 pieces that we can use to find our derivative here in the red, right? We now have h, h prime, g, and g prime, which is what we need. So I need h prime. What is h prime? Write it up here. H prime is 1 over g. What is g?
The 3x minus 1 over x plus 2.
Times g prime of x. This is an answer. I'm looking at an answer right here. I can simplify it, but this is a functional answer. I have now put all of the pieces together that give me my derivative. What can I do with this here? If I have 1 over a fraction, like if I have 1 over 1 over 5, what is that equal to? Going to be equal to 5. So if I have 1 over a fraction, then I can rewrite that as x plus 2 over 3x minus 1, reciprocal. Right? Then I'm going to multiply it by 7 over x plus 2 squared. Look at that. I can cancel that. And now, what was that?
Sorry, I just got lost with that. Would we put the, is it the top 1 over 1 over 3x minus 1 over x plus?
I mean, I guess you could write it like that. This is something that a physics teacher actually taught me. He called it like jumping the fence. And if you see something of this form, you're able to just quickly like think about like, I'm going to put it up there. But if you want to write it like this, 1 over 1 divided by 3x minus 1 over x plus 2, how would we solve this? Well, I don't want to deal with a divided by. I want to deal with a multiplied by. So if I want to multiply by something, I need its reciprocal. So I'm going to turn that to a dot instead of an x. Multiplied by x plus 2 over 3x minus 1, which is something that you told me to do like an hour ago. All right?
Yeah. So jumping the fence, that's a pretty easy way to do it, is just to take the denominator of the denominator and just move it to the top.
Yeah. But if you have any doubt, then just set it up like this. It takes you an extra 10 seconds. And it may save you some pain if you're concerned about what the content of an answer is. But yeah. So 1 over 1 divided by this. So it's 1 over 1 times the reciprocal. And that's how we end up with what we end up with. Okay, so now we're looking at x plus 2 over 3x minus 1 times 7. I have x plus 2 squared, which is x plus 2 times x plus 2. I can cross that off. One of those x plus 2's down there. My final answer is going to be 7 over 3x minus 1, x plus 2. I could FOIL that, but I don't really need to because there's really nowhere else to go in terms of simplifying this. Okay, what does it mean? What did I just get? Let's set this up here and explicitly say what I did. I said a relative rate of change is equal to the derivative of the natural log of the original function then I said that that derivative is equal to this right here. Okay? Everybody's okay with what I just wrote down?
Yes.
Awesome. Sorry, I wish I had like unlimited board space. Okay, so I have made that statement. Now, this is the relative rate of change for this function. Now I want to say, what is the relative change? When x equals 1. How do I find that? Well, I've got here, I would find the derivative of this function, and x is equal to 1. So I found the derivative, and now I say x is equal to 1. So it will be 7 over 3 times 1 minus 1 times 1 plus 2. So 7 over 3 minus 1, 1 plus 2, 7 over 6. Thoughts, comments, and concerns?
My nose is bleeding a little bit.
Oh no, really?
No, I'm just kidding. It's just like, oh my gosh, this is so
This is a really scary one to start off.
Yeah, I was trying to go, yeah, but I mean, it's good though, because
It is.
it really covered just about everything in the quotient rule.
It did.
Is there a difference in the product rule?
The product rule is just a different rule. So if everyone's okay with this, I'm going to clear this. And we can say that the rules that you need to memorize, this is something that you will need to memorize for your tests. It's going to be the chain rule. which is if I have the function f of g of x, then the derivative of this is not. The derivative of that is going to be f prime of g of x times g prime of x. The product rule which says if I have a function f of x times g of x, the derivative is equal to f prime of x times g of x plus g prime of x times f of x. And then you have the quotient rule. Which says I have the function f of x divided by g of x. I want the derivative of this. It is going to be f prime of x times g of x minus f of x times g prime of x, or we could say g prime of x times f of x divided by g of x squared. So this is stuff that you're just going to want to memorize. These are the rules that you're going to just need to know.
Okay.
Okay. Any questions about these rules? These are applicable to essentially anything. You just need a function, and you can make these rules work. Sorry, 1 second. I need to check my email because technically I have something that would be starting at 5. But if nobody is going to be there, then we can just continue here. And it looks like nobody's in this. So I'm just going to check my email every once in a while, and if somebody pops up in the other Zoom room, I'm going to have to go and help them in a different class. I shouldn't have scheduled these so close together. I might be shifting around the schedule in the next week or so to accommodate that. But let's do some simpler problems, because what we just did was a huge monster. Let's do something that's not a huge monster. Let's do something that shows you that you can use these rules. So I'm pulling these straight out of the book. These are all things that you are able to do, and I promise you, you are able to do them. Our numbers might differ because, again, I'm still on the old edition of the book. But I have in section 3.5, I have problem 9. Actually, we're not going to do problem 9. We're going to do problem 10 because I was going to set that up to do something different. Not problem 10. Let's not do that. Let's do problem 18. Okay, so we have a function f of theta is equal to theta cubed cos theta. What's going on here? What 2 functions do I have right here?
What are they asking us to do?
Take the derivative.
Okay.
I can split this into 2 things.
Would it be theta cubed, and then the other one would be cosine theta?
Yeah. I'm calling that G and H. What am I doing to these two functions?
The left one, wouldn't that be a power function? So it would be 3 theta and squared. And then the one on the right would be negative sine theta.
Bingo.
Wow, I actually just did that from memory.
Yep, you did. So now here we are. But what are we doing in F? How do we put these together to find the derivative? We have all of the pieces now, but you got to tell me how to put them together.
I don't know which rule to use.
What am I doing to these functions? Read this aloud to me.
Are they being multiplied?
They are being multiplied, which means that they are a product.
Product rule. So it would be f of g, or f prime times g plus g prime times f.
Exactly. In this case, we don't have F, we have H. But yeah. So we said this is theta cubed times cosine theta. If I say times, it means I'm multiplying them, which means that they are a product. Then I get to put it together in this way. Because it's the product rule, this could be H prime G plus G prime H, or it could be G prime H plus H prime G. We're adding them. It's commutative. We can do whichever one first. I wrote it like this, so let's do it like this. That would be minus sine theta times the original G, which is theta cubed, plus the derivative of G, which is 3 theta squared, times cos theta. And you can probably shift this around if you'd like to. You could rewrite it as minus theta cubed sine theta plus 3 theta cubed squared, excuse me, cos theta, but there's really nothing more you can do to really simplify it. And I would call this a great answer to what is the derivative of the original function.
And that's an acceptable answer?
That's the answer. You're done. And you used the power rule, you used your trig functions. You did it. So, I promise you these are things you can do. What about a really simple version of this? What if I have I have z is equal to cos 4 theta. Why do I keep using the theta ones? I hate drawing thetas. They always look like little, I don't know, like sigmas, because I'm really bad at them. But I'm calling this x. I don't care anymore. We're just calling it x. It's 4x. What am I doing here? Do you remember they gave you a rule for this in 3.5, but you don't need to use the rule because you know the chain rule.
Oh, so this would be the inner and outer functions. Cosine would be the outer function and 4x would be the inner function?
Yep. F of g is going to be cos g. F prime of g we need. And then the inner function, we literally can just say, hey, we have g of x is equal to 4x, and g prime of x is equal to 4. Do you remember what the derivative of cosine is? I just had to do this. Nice.
It's negative sine x.
Yep. Okay, I have 4 different pieces. I can set this up as the function f of g of x. So I am looking for the derivative, which I'll say is dc dx. Sorry, I like using Leibniz notation because I think you guys are a little bit uncomfortable with it. I've gotten that feedback before, and it is very explicit, which means that it's something that I hope that you guys can get comfortable with. So the derivative is going to be f prime of g of x times g prime of x. That's what the chain rule is. I go from here to here. So we can put it together. I have the function f prime of g is going to be, I'm going to do it in 2 steps. I have sine of g, and then I'm going to multiply it by g prime, which is 4. So I'm going to turn this into minus 4 sine g. But I don't like having that g there. That g does not belong. My actual g, I know I defined it up here as 4x. So I can rewrite this as minus 4 sine 4x. And I think what they said what they gave you in section 3.5 is they said if you have the derivative of cos kt, where k is a constant, then it is equal to the negative k sine of kt. So they give you this as a rule, but it's literally just using the chain rule. In a very specific instance when you have a singular, you have like x to the 1, t to the 1. Does that make sense? Because this is like last week's rule and then this week's rule, and they're the same. It's just last week's rule is more explicit.
Yeah, that makes sense.
We could continue to do problems like this, where we make g grodier and grodier. Instead of 4x, I could give you, I don't know, the square root of 5x times x cubed. No, plus x cubed. Here, I'm going to erase this. I can give you something that looks like this. Z is equal to cos of root 5x plus x cubed times the natural log of x. Does this look like a nightmare? Yeah.
Yes, it does.
But you can do it. You just have to keep breaking things down. What's the first thing you're going to need to do?
The outer function and inner function?
Yep. What's your outer function?
Would it just be cosine?
Mm-hmm.
Is that square root over everything?
Yeah. Why not? We're not actually going to solve this. I just want to break it down for you so you can see how you can break it down. We don't actually need to solve this. But then what is g? If your outer function is cosine, then your inner function
would be the whole thing?
Yeah. Which we're not going to write as a square root because we have a better way to write that. and it is to the half. So if I have a bunch of stuff that is to the half, what am I going to need to do for G prime? What rule am I going to need to use here? I have a bunch of stuff in the interior, and it's all to the half.
Would it be the power rule distributed to both terms?
Not actually the power rule distributed. It's, again, we're going to use the chain rule, where, I don't know, we'll call it h of x. We'll call it j of h of x, where j of h is equal to h to the half. So now we can use the power rule, but on the interior, we're going to need, do this, and I want to keep the colors kind of consistent so that we can follow. So our interior function is going to be h of x. And h of x is going to be equal to 5x plus x cubed times the natural log of x. So I would need to find j prime. I don't actually care right now. But I would also need to find h prime. How could I break that down? What do I have here? I have a function times a function. So I could call that m of x times, running out of letters, q of x.
So you're doing a chain rule on a chain rule?
Yes. And then I have a power rule. So this would be m of x is equal to 5x plus x cubed, and q of x is equal to the natural log of x. And from here, I can say, so what I have is I have a product inside of a function and then another function on the outside. So I need to do the product rule and then the chain rule twice. It wouldn't be pretty. I wouldn't want to do it. But if you can do a problem like this, then you're set for anything they throw at you on the exam. Because you've got 3 different layers of things going on here. You don't actually need to solve it. I just wanted to show you that you can break it down into something like that. Okay, I think I'm going to say, please feel free to ask any questions you need to in order to kind of get a better understanding of this.
Could we, there's a problem that really threw me. I understand everything from the I think it's 3.4 and 3.5, but from 3.3, it had a negative exponent that just, it threw me, and then I just kind of did it wrong because of the negative exponent.
Hit me. What are we doing?
It's f of t equals 6.8 e, and the exponent on the e is negative 0.5 t.
Okay. What rule do you think we're going to be using? They give you something to use here, kind of like what we just did with the trig function, but there is a rule that makes this make sense. What rule do you think it is?
Is it the relative rate of change, where it's the d over dt and then ln?
Is this asking you for the relative rate of change?
I believe so.
Okay. That's like a step to the problem. So if the question is a relative rate of change problem, then you use the equation And in order to use the equation, you need to use the chain rule. So if you want to do this as a relative rate of change problem, then we're going to need the chain rule twice, because we already need the chain rule to solve this. You can ask me to just find the derivative of this, or we can do the chain rule. It's up to you. But the chain rule is going to, now we've got two chain rules. The relative rate of change problems are really tough because they're forcing you to use the chain rule, and if you already have a tough function in the middle, then it gets really roady.
Yeah, it was the relative rate of change, and it was forcing for the formula.
So we're going to use the formula. The formula, as we established, is going to be the derivative of the natural log of f of t. What is the first step that you would have me do? This is equal to the relative rate of change. So
it would be to identify the inner and outer function?
I would start by setting this whole thing up. I would say the relative rate of change is equal to the derivative of the natural log of 6.8 e to the minus 0.5 t. Now, there are two ways we can play this. Number one, we can be smart about it, and number two, we can power through. Powering through would be to say, I have an inner function, which I'll call g of t, that is equal to 6.8 e to the minus 0.5 t. I would find g prime of t, which would require chain rule. Then I have my outer function, which is the natural log of g. And by require the chain rule, I mean we need to move this constant down, which involves the chain rule. That is the brute force method. Do you have an idea on what the, I'm thinking about what the other method might be?
I honestly don't, I don't know.
Red flag, I have a natural log and I have an e. So the way that they likely want you to solve this is not by brute forcing it, but by saying rules of natural logs. So that would mean that I have, let's see, natural log of something times something. Am I confusing my rules of natural logs? I don't think so. The natural log of a minus the natural log of b is equal to the natural log of a over b. That means that the natural log of a plus the natural log of b is equal to the natural log of a times b, which means that this is the derivative of the natural log of 6.8 plus the natural log of e to the minus 0.5 t. Okay, so that's my first. This is a rule of natural logarithms. I don't know how familiar you are with natural logarithms, but this is something you might want to know because it is going to make your life easier and you won't have to brute force something like this. Then what you want to say is, okay, I'm sitting here, I have a natural log of e, but it's still 2 something. And then what you can do with this is the natural log of e to the something is equal to something times the natural log of e. This is actually true of any base. It's not just e. This is 2 to the something. Any base. So I'm going to move that down, and this is going to become the natural log of 6.8 plus minus 0.5 t times the natural log of e. What is the natural log of e?
Is it just e?
Nope. If we think about, what if I have x and I multiply it by 2 and then I divide it by 2? What do I get?
Would it just be x?
Yes. That's because multiplying by 2 and dividing by 2 are essentially opposite functions. Opposite functions in this case is going to be the natural log and e. So taking an exponent of something is essentially the opposite of taking the log of something, which is not nearly as intuitive as like multiplying and dividing. But this is something that I can say, and it is that the natural log of e is equal to 1. And e to the natural log of x is going to be equal to like x. Yes. Yes. That being said, the natural log of e to the x is equal to x natural log e, or x times 1, right? This is 1. So this is 1. Then what I'm looking at here is the derivative of a constant. This is just some number plus the derivative of minus 0.5 t. So this is some number. So the derivative of some number, derivative of 2 is 0, the derivative of the natural log of 6.8 is 0. Constant number. Plus the derivative of 0.5 times t. What is the derivative of this?
Is it just negative 0.5?
Perfect. So the relative rate of change is negative 0.5 in all cases.
For the ln 6.8, 2 steps above the answer, that one is 0 because the derivative of it is 0.
Yes. I split this up. I said the derivative of a sum. Here I have the derivative of 2 things added together. And then I said that is equal to the sum of the derivatives. So I have the derivative of the first one plus the derivative of the second one now.
So the derivative of the first one is ln 6.8.
So I split it into the derivative of the natural log of 6.8. I'm saying that these two are equal. I'm saying that the derivative of the natural log of 6.8 plus, or rather minus 0.5t is equal to the derivative of the natural log of 6.8 plus the derivative. Doesn't look as clean if I wrote it out in this way. If I said that I want the derivative of the natural log of 6.8 minus 0.5t, you would know what to do with this. You would take the derivative of the first, which is 0, and then the derivative of the second, which is minus.
I guess that's where I'm confused, where the derivative of ln 6.8 is 0. The rule that I have for that is if it's ln x equals 1 over x.
Yes, that is for a variable. So if I have ln x, it's equal to 1 over x. But is this a variable? It's just a number. So if I go into my calculator, which I'm doing right now, and I say I want the natural log of 6.8, it spits out a number for me. The natural log of 6.8 is equal to 1.917. So what if I wrote it down like this? I want the derivative. So this, I'm saying this same thing. 1.92 minus 0.5 t.
Because it's a constant, it's a number. That's why there's no slope to it. That's why it's 0.
Yes. Same thing would be the case if I had e to the 2. That's essentially like 2.7 squared. Just a number. Does that make a little bit more sense? I know this is like probably not what you were expecting when we started this problem, but this is the best way to solve it.
No, it's making sense. How would I know when I'm looking at the ln 6.8? How would I get that it's 0, but how would I know looking at it that I wouldn't just, because my natural instinct is just to take the 6.8 and put it 1 over 6.8.
So the way that you would know is by asking yourself what the variable is. Okay? So if this is a function of t, then you need to differentiate here with respect to t. We're only looking for t's. So if you're looking at a function, I don't know, if you had the derivative x cubed plus 2x squared plus 4, the way that you know that you are like going to end up with 3x squared plus 4x plus 0 is that you're only looking for the x's, right? What if I had something that looked like this? And I keep doing these separate examples because I think they might be easier to look at than working with natural logs. And I want to say that the same rules apply to everything that we've been doing as to natural logs. So what if we had the derivative of x, ax squared plus bx plus c? What is this derivative?
It would be a2x plus b, and that's it.
How did you know that?
Because c is a constant, so that doesn't have a slope. X is just x to the 1, and then it's x1 minus 1, and then I'm going at it backwards. And then a to the x2, the 2 goes in front of the x, and then it's 2 minus 1, which is 1, and x to the 1 is just x.
So you knew that you were working with x.
Correct.
You were fully aware that x is the variable here.
Yes.
So in that same way, you're looking for t in the red. And if there is no t, then you can't use the natural log rules for derivations because it's not. I'm going to do something that's going to be really weird. What if I had not d dx, but d db?
Then I would only be looking at the second term.
Yes, because a is a constant, x is a constant. That zeroes out. C is a constant. That zeroes out.
Oh.
Now, x is a constant, b to the 1. What is the derivative?
You said x is the constant?
X is a constant, which b is the variable.
Then the x wouldn't have a slope, so it would just be b?
B is the variable. So b is like what x used to be. So this is now a function, I don't know, I'll call it f of b, that changes when b changes. So if x is constant and it's b to the 1, then we use the power rule on b, not x. So it'll be b to the 1 minus 1 times 1 times the constant. So what am I going to end up with?
Oh,
And this is-
is it just x? Because you said b is the variable, right?
Exactly. So it's a really convoluted and roundabout way of me telling you that you know how to recognize variables in these problems. There's a reason people don't use x as a variable, or rather x as a constant, and it's because everyone assumes x as a variable. So this was kind of a cruel way of me setting this up. But if b is my variable and x is constant, then this is what it looks like.
Honestly, until this example, I was not paying attention to the letters when it's oh my gosh, I don't know what to say. I'm trying to say it. I wasn't paying attention to the letters when it says trying to find the slope, I guess, or d over db or d over dt. I wasn't paying attention to those.
They can give you whatever letters they want to, essentially, which is like not very nice of them, but they can. They won't make you do something like this, where they come at you with a ddb of a function containing x as a constant. But that is basically what's up. Also, you don't ever need to worry about multivariables, but this is like something that you can extrapolate to functions of multiple variables, which I urge you not to think about. But yeah, I hope this is a little bit better for you. Do you have any more questions, comments, or concerns regarding this stuff?
No, and just so I understand, if for some reason I get kind of freaked out if I see a problem like this, I could just kind of force it instead of going through the rules that we went through to really make it simple.
The natural log rules make it simple, but you can always just say, I have a chain rule function, I have a natural log outside function, and an inside function that looks like 6.8 e to the minus 0.5 t, and then do it that way. And that will give you the same answer. It will just take a lot longer.
Gotcha. That makes sense.
Okay.
Can we run over just the quotient rule just very quickly? I know you have to go.
No,
I just
that's
want to make sure that I have the formula correct.
Yep.
If I see f over g in a problem, or f over g prime, then it's just f prime times g minus g prime times f over g squared.
This is exactly the formula. Yes. So the derivative is equal to this. You got it. However, it's always going to be g, not g prime in the denominator, and f, not f prime in the numerator of the original function. Because basically what you're saying is, I have this function. I want its derivative. In order to find its derivative, I need all of these different parts. But you're not going to start with a derivative. At least, yeah, you're not going to start with a derivative in this section, essentially.
Okay, that makes sense.
But yeah, you're right. Did you want to do a quick example here?
If you have time, I would really appreciate it.
Yeah, for sure. Okay, let's see. I marked down a couple of problems in this section and I never got to. Rip. How about this one? I have it as problem 24, where I have this function w of z is equal to 3z over 1 plus 2z. So what I want to find is dw dz. And the way that I read this is the derivative of w with respect to z. I can always tell what my variable is by looking here. or looking here. So walk me through this. Tell me again, what is the quotient rule? Just like literally list it out to me.
Okay. Let's see, it's F. So 3Z would be.
Oh, you literally can just give me the F over. I want to just write that down so that I have it written up here in this corner.
Oh, F prime times G minus G prime times F over G squared.
Yep. Okie doke. So we have this now. Tell me, what is F?
F would be 3Z.
What is F prime?
1 plus 2Z.
F prime?
Oh, sorry. It would just be 3.
And G?
1 plus 2Z. And that would just be 2 for G prime.
Perfect. Okay. Now I need to put it together in this order in order to find the derivative. So this is going to be equal to F prime. What is F prime equal to?
3
Times
G is 3 times 1 plus 2Z minus 2 times 3Z over 1 plus 2Z squared.
Perfect. Then what we do is we distribute like this. So we end up with 3 plus 6Z minus 2 times 3Z is 6Z over 1 plus 2Z squared. These are going to cancel. So dW dZ is equal to 3 over 1 plus 2Z squared.
Would it be wrong in the previous step would it be wrong in the previous step to cancel out the one of the 1 plus 2Z's in the denominator and then one of the at the top?
Yes, that would be wrong. Because what we need in order for that to happen is an extra 1 plus 2Z. So that essentially you can't think about it like this. I have something on top minus something on top over the same thing in the denominator. I can break this into 3 times 1 plus 2Z over 1 plus 2Z squared minus 2 times 3Z over 1 plus 2Z squared. If there's something on the denominator, I can't break it up like this, but if you think about it in terms of like, okay, I have 3 divided by 4, I have 3 minus 1 divided by 4. This is a really simple example, but we could solve it by saying this is 2 over 4, or we could say this is 3 over 4 minus 1 over 4. Are you good with what's in the pink?
Yeah.
Okay. So that's something that we can do. Just as a side note, because I want to make sure this is clear, if I have 3 over 4 minus 1, this is not the same as 3 over 4 minus 3 over 1. You can't do it if it's in the denominator. But you can if it's in the numerator. So because the minus sign is in the numerator, we've split it up like this. Then, if you wanted to do that, you could cross out this, and you would end up with 3 over 1 plus 2Z minus 6z over 1 plus 2z squared.
Gotcha. And then it wouldn't work out because we have to have a common denominator.
Yes.
Okay, that makes total sense.
For sure. You know these rules. I know you do. It's just like a matter of like, gosh, like there's so much happening. How can I think about this in a way that is simple enough for me to like process? Which is why I break everything up and write everything down. If you remember in those earlier problems where I was getting into like, you know, Q of X, that's ridiculous. But it's the only way that I know how to keep organized in all of this. So that's why I do it.
And that makes total sense now, especially the colors are really helping because it was just extremely confusing and I was getting very worried.
Yeah, I think the colors are pretty helpful. I sent you an email also, didn't I? Last week, there was a problem that you were having trouble with.
Yeah, you did.
Did that help? I don't actually know. I don't know if I got a response from you.
Sorry, that was really rude.
I know,
yeah.
It's literally a problem.
It did help. I was able to use it to solve, but I didn't understand the logic behind it. I was able to do it and use it on the test, I guess the logic behind it, but I didn't understand how one number above the inequality was able to give me the answer.
Okay. Let me.
I know that's kind of confusing.
Okay. I'm gonna put it. One number above the inequality. We set up that inequality. Oh, basically what we're saying is, I think I understand where your issue was, and I actually am going to call back to marginal cost. Are you a business major?
Unfortunately.
Okay. I sometimes get ag students in this class, and they don't care about marginal cost at all. But as a business major, you probably do. So if I have a cost of, I don't know, Q, and I want to find the cost of Q plus 1, and I only have the cost of Q and the marginal cost, what is the cost of Q plus 1 equal to?
I don't know, and I just want to be upfront. This portion of the textbook, I did not understand anything. All that I got out of it was that anything above an additional cost and additional revenue is marginal cost and marginal revenue. That's all I got out.
So, the cost is C of Q, right? This is the cost to produce Q units.
Yeah.
Then I have C prime of Q. This is, what is a derivative, first of all? 3 words to describe a derivative. ROC, rate of change.
Rate of change, okay.
Rate of change of the original function, which is cost. Okay, so what is the rate of change of cost? The way that we think about it in terms of the cost and revenue functions is that, okay, what if I had Q objects and I wanted to make Q plus 1 objects? I don't know what we're making. I'm not a business major. And but the idea is that we need to go from Q to Q plus 1. So this is C, this is Q. So it's going to cost more. This is going to be C of Q, right? And this is going to be C of Q plus 1. Are you good with me here?
Yes.
Awesome. So it's going to be an increase. What is this?
The rise would be q plus 1 minus q, or c of q plus 1 minus c of q.
And then the run?
Q plus 1 minus q.
Okay. So now we found the slope, right? I'm going to write this down as c of q plus 1 minus c of q over 1. So it's literally just c of q plus 1 minus c of q. And the idea is that is, I'm like trying to think of a good way to say this. That is going to be, the difference between these two is going to be the rate of change. Because if you think about a rate of change in its most simple thing, we're thinking about a slope, right? We're thinking about a rate of change. What if I had 990 items and I wanted to make 991? And I don't know what the difference is. Like, I want some way to go from the cost in dollars here to the cost in dollars here. I have one object. Do I have some way, something unit-wise? This is going to, C of Q is given in dollars, right? I'm really like all over the place right now. I'm so sorry. Let's focus. What is the units of C prime? The rate of change of cost.
Yeah.
What is the units of this? Is it dollars? It's a rate of change, so this is in dollars, and this is in objects.
Okay.
Right?
Yeah.
So why don't we think about it like this? This is the dollars to add per one object. So if I had this is equal to 40, then this would be $40 to make one additional object. Does that make sense? To go, the difference here is $40, one object. My slope is $40 over one object.
So it's $40 to make one object?
One additional object. From Q to Q plus 1.
Okay.
What did I just describe?
The relative rate of change?
Not quite. This is just a rate of change. But I have this special condition where I'm only going from Q to Q plus 1. This is the marginal cost, which is the cost of adding one more object. There's a better word for that. I don't remember what it is, and I'm sorry. But the marginal cost is the cost of adding one like additional object. It is the rate of change here. It is the slope, and it is given in units of dollars per one object. So we say that the marginal cost is the same as the derivative of cost. We can see where we get the units and ignore this because that's nonsense, I've decided. Does that make marginal cost make a little bit more sense?
Yeah, so marginal cost is the cost of adding more objects than what was already produced.
One more object.
One more object?
Yes.
Oh, so marginal cost is only related to making one more object.
Yes. And the reason that we say only one more is because the rate of change in a function that looks like this is not going to be the same here as it is here. And if you draw a line between these two, you're not looking at a very representative like sample, essentially. Like this average rate of change is not very representative of the actual rate of change at any of these points. So it becomes a question of average rate of change, which is that, and instantaneous rate of change, which is the slope of the line tangent to the curve at a point. Right?
Yeah.
So we know that instantaneous rate of changes are better at telling us what's going on. I don't know, being accurate. Than average rate of change. But what's the condition for an instantaneous rate of change? It's only accurate in this little area. There's a very small q. This is still the q axis and the c axis. So it's only like q plus 1, and q minus 1 that this instantaneous rate of change is accurate for. Does that make sense? Because if I applied this average rate of change over here, how good is that slope at saying what's going on this line at this point? Really, really bad. So we only want to use it nearby, which is why the marginal cost is always per one object. And it's because it's the rate of change, but it's an instantaneous rate of change, so we want to keep it really close to the object that we took the differential by, the derivative of that. So if I found c prime of q when q is equal to 4, then the marginal cost would be the same, but you want to have it conditional that that's the marginal cost of adding one more object when the objects are going from 4 to 5, essentially. Are you okay with all of this?
Yeah, it's making more sense.
Okay. So the reason I bring that up is because, hey, what if I have the cost of q plus 1, and I want to find it? That'll be the cost of q plus one object times the marginal cost, which is measured in dollars per object, right? So my units work out. Cancel out objects. I guess not really a physicist. So this is like a science thing, I think. I'm a STEM major, so I think about what are the units of this thing, because that is what makes a lot of sense to me. But basically, this is 1 times the marginal cost. So my answer here is my original cost plus my marginal cost. If I have, here is 40 objects, and here is 41 objects, and here is $980, and here is $990. Then the cost of adding one more additional object is going to be the instantaneous rate of change at this point. Maybe it looks like this. Maybe it's a really weird looking curve. So the curve is not like a straight line, but at this point, it's fairly accurate to say that the marginal cost is $10 per object. And the reason why I was able to do that whole f of 11 is equal to f of 10 plus f prime of 10, which I think is what you had the problem with, is because of the exact same reason I can do what I'm doing here. This is c of 41 is equal to c of 40 plus the derivative marginal cost, which is C prime of 40. So back to the initial problem that we were discussing. The reason I can say this, and this is not exactly right, it's like approximate.
Yeah.
That's the reason. And this is the form that you're more likely to see this in this course.
Okay, that makes, so that's why it was just the one that was additional, because it was the marginal cost of one extra object, because the rate of change would be different at different.
Yeah. So I couldn't say that like f of 14 is equal to f of 13 plus f prime of 10, because this is too far away. But when it's close enough, we can make this approximation. And I ran out of room on my tablet. Okay. Unfortunately, I do have to go now.
No, thank you very much. I appreciate it.
Thank you very much for coming. I hope you have a wonderful evening. I don't know if you follow football, but Penn State plays in like an hour, I think. And I don't know. I've heard it's a huge game. I'm not a huge football person, but
neither am I. But I was going to watch it, but now I have to go to the hospital because my daughter just fell off a horse.
Oh no! I hope she's okay.
Yeah, she doesn't ride horses. So I'm very surprised. My wife took her out. I know she was going to the cider mill over in, I'm in Michigan, so my cousin has a farm. I didn't know. So I'm very surprised.
Wow. I really hope she's okay. That can really hurt. I've done that before, and it's not pleasant to fall off a horse. The hospital. Wow.
Yeah, I'm very surprised. That was, I don't know if you heard my phone went off, but that was my wife, so I was waiting for her to call me back to tell me where they were going.
Oh my gosh. Well, yes. I have your daughter in my thoughts. Wow.
I'm sure she's fine. It's just like, how does that even happen? But I don't know.
Yeah.
I guess it's fine.
Okay. Well, I hope your night gets better.
I'll try to check out the game.
Gets better. Have a good one, I guess.
Oh, well, I appreciate it. Thank you. I'll check out the game, and I really appreciate the help, and I really, really appreciate the extra time very much. Thank you so much.
Of course, of course. You have a wonderful weekend, or as best a weekend you can talk in the hospital.
All right.
Bye. Thank you for coming.
Thank you.